This lecture is going to focus on integration using the antiderivative. Okay, so let's just review a function. Phi is an antiderivative of fx on the interval provided that the derivative of the antiderivative equals the derivative. So again, we're given the derivative and we're trying to find the antiderivative. Okay, that's the issue here. All the antiderivatives look like each other except for a constant. So if you find one antiderivative, you know them all, right? Just add any constant to them. So there's infinitely many antiderivatives, and they all differ by a constant. And well, the set of all antiderivatives is denoted by this notation, the indefinite integral. Okay, this is a set. You need to understand that, and I'll emphasize this in the problems when we work them more carefully. This is, in fact, a set of functions, and they all look like this. They all look like one base generator principal function, root function, plus some constant, right? The constant can be all possibilities. So they all have a particular structure, and again, we'll explore that more carefully in the problems. So these are the base concepts. Okay, so here's the idea. Your function that you're looking for that's going to satisfy the particular initial conditions is going to be an element of this set. We write the set in different ways. Again, it's for the usage of it. You could argue why so much trouble. The highlighted way here kind of makes it look like this function looks like this particular form. But this is, again, a set. This is just kind of a misleading notation. Again, once you're comfortable with it, it's no problem. But it's not. This is not a function. This is a set. Okay? So again, everything in this set, all the functions in this says the set of f is an element of differentiable functions, right? Because we have to take its derivative on alpha beta, such that our function equals this base function plus some particular constant. So again, it's just a notation. For me, this isn't standard. Again, I'll tell you when my notation isn't the same as everyone else. I just use, to make it easier for you to see, when I'm talking about a set, and if I use this form, I use a capital C. And when I'm talking about a particular function in this set, I use a small c. So small c is like we did x equals a. A is an arbitrary but fixed point. C here is a constant. You have to tell me what it is. Okay, this will never say what this is. This is just a notation for a set. Again, you'll see when we work problems more carefully. So again, C has to be particular numbers in this set. Now, just working as we did in the last section, the antiderivative section, 2 sections ago, these are just the differentiation rules stated as antiderivatives, right? So we have a constant rule. We can take the constant out in front of the set. So this would say that a constant times this set is the same as the set with the constant inside of it, right? This is a set. So this is really just properties of sets, that you would have done a number of years ago. Again, this is really saying this set union with this set, right? You're putting these together. Adding this set plus this set is equivalent to this set, and so forth and so on. But we could just use them formally. You don't have to make a mountain out of it. Integration by parts looks like this. We're not really going to do this in this course. This is where Calc 2 usually picks up. I will spend my last lecture talking about this because this is decisive in terms of doing actual computational work. There's no equivalent to the quotient rule for integration, and we have the substitution rule. So we'll spend the last few lectures actually dealing with the substitution rule. So we're primarily going to look at the constant rule, sum rule, difference rule now. And then these are the particular rules. This is the power rule written in integral form, anti-differentiation form. This is, again, the sine, cosine rule, e to the x, and 1 over x. Okay, so These are the particular rules we have. So again, these are the rules of the game. If you're going to make a move, just like with differentiation, there has to be a rule underlying what you're doing. All right, so let's take a look then at some problems. So again, here's a problem stated. So let's be clear what we mean by this. Okay, so I'm going to emphasize this. When you write this, we're saying that our derivative is in fact here, 3x squared. This is the derivative, right? And we're saying our root antiderivative, or our generator, or again, different fields have different names for this term, is x cubed. Right? That's what this statement gives us. This is the derivative. We're trying to find the antiderivatives, and all antiderivatives have this basic form. There'll be this root plus a constant. This again, this is a set, right? This is a set. So you have your base 1 as x cubed, and plus the constant is 0. And you have every single possibility of constants in here, dot, dot, dot. So there's infinitely many elements in this set, and they all look exactly the same. And I prefer this notation. Again, this isn't entirely standard. I prefer this notation, but I'll show you. You don't have to use it, and it's more than fine if you don't. Again, this is really more me than the rest of the world. I'll tell you why. Again, this particular element is called the representative element, the root element, or the root function, the generator, the principal. Different fields for their own particular needs wind up calling this particular element a number of names. It's the one essentially where the constant is 0. But again, it doesn't have to be. You just need any one and you can get them all. Okay. Every function in this set, notice, every function in this set looks like this root element, or this generator, plus some particular constant. Here the constant is 0, the constant's 1, the constant's minus pi, the constant's 3. So everything in this set has this same basic form. And moreover, if we take the derivative, right, this is an antiderivative. If we take the derivative of the generator or the root, we have to get back the original derivative function. And this is good because this is a good way that you can check your answers on these problems. So you'll get an answer, take the derivative, and see if it's correct. And I'll emphasize that in the problems. So these are the features, right? These are the features of what this looks like. So let's talk about actually solving this problem. Okay, so here's our original problem. And again, you should think of this as we did the same exact steps with differentiation. Now we're going to do the same exact steps for antidifferentiation. So look at this and see, what is the rules? Okay, you can use your crib sheet, and I highly encourage you to follow me. There's only one rule that applies here, right? There's only one rule that applies here. You don't have any flexibility in what you can do. Again, this isn't, I'm asking for your opinion. I'm asking you to be creative. Creative is over now. We did the fundamental theorem of calculus. That was where the brilliance came in. Now you're nothing but a technician. You're not doing anything. Apply the rules. So again, what rule applies here? Pause the video and check that. Okay, so it's going to be the constant rule, right? We're going to take the 3 out in front of this set. So every element in here has a 3. We're just going to take it out in front. Now again, if you look at the next piece, what's the only rule that applies here? Okay, pause it and take a look at the crib sheet and see. Okay, it's going to be the power rule. Again, it's the only rule that applies here, right? So my power is 2. Now again, I'm not saying you have to write these out, and you should certainly have it in your mind how this works, right? So it's the power rule. And then it's just a matter of cleaning up the algebra. The 3 can come into the set again, and you clean that up, and it's just this. Now, again, this is the way I'm going to emphasize it, because what I've found, in teaching calculus is people have a lot of trouble keeping this constant, what to do with this constant. And, again, it's just a distraction that I feel we don't need. So these are the steps using the notation of the sets in this way, and this is the typical notation maybe that you're used to. I just don't think that this notation helps. There's a lot of confusion with this. So example, why don't you distribute the 3 times this and the 3 times the c? Well, because what this means is it's just a constant for the set. Right, it's a constant involved here, and I talk about it later in one of the examples or now or something, but we'll get to that. But this is why there's difficulty with this, and that difficulty doesn't happen with this notation. So again, this notation is fine if you're comfortable with it, but I find most students aren't. But regardless, these steps mean exactly the same thing. All right. And once again, what I can do is I can change out, I can check my answer, right? The derivative of the generator equals my original antiderivative. Okay, so let's look. So this is my result. And again, this is the template. You'll see that this is the way we're going to do the problems. And we're just going to work a lot of these problems out in future, right? So we're going to do a lot of these, but this is just to set everything up. Now the other kind of problem we're going to explore is the initial value problem. Now we looked at this in the antiderivative section a couple sections ago, and really looking at it in that way, just reverse engineering the differentiation rules is pretty tough. So let's look at this more carefully. Here's my function, my antiderivative. Here's my initial condition, right? This is the standard initial value problem. So let's take a look at this. So my original, my antiderivative is this, and my initial condition is here. And let's just go through it, right? We need a particular antiderivative of the derivative that satisfies this initial condition. So the first thing is to simplify the function we're given, the derivative, right? We're going to put it in the form, and you'll notice all the rules apply to basically we want constant times x to the power, constant times x to the power, sine, cosine, e to the x. I mean, that's essentially all we have. All right? So the first step then after simplifying is find the general solution. Again, the general solution, it sounds like it's just a function. But the general solution, again, it's just the terminology we use. It's mainly not accurate, but it's what we're talking about. So the general solution is the indefinite integral of our derivative, right? And it's this notation. It's really a set. So the general solution is really a set. Now you'll hear people when you go into engineering math, this is the kind of problem you're essentially going to be looking at. You hear people constantly refer to the general solution as a function. It's not a function. It's a set of antiderivatives. Okay, so here's our function. Here's our derivative in here. We're trying to integrate it. Now again, the same rules are going to apply here. Look at this and what is the only rule that applies here? What is the only rule that applies? Right? It's going to be the difference rule, right? The only rule that applies is the difference rule. So notice this is very, very similar to what we did with differentiation. It's basically based on the same rules, only just going backwards with them as I explained in the antiderivative section. So now we've broken into 2 problems, and you have to do each of these. Now, if you look at the first term, what's the only rule that applies? Again, take a look at the sheet. What's the only rule that applies here? The constant rule, right? It's the only rule that applies. Okay, so now we look at these 2, or look at this piece or this piece, and again, what's the only rule that you can apply here? The power rule, right? The power rule applies here. So in this case, the power is 4, right? So just plug it in. And in this case, the power is, right, minus 1/2, right? And now you just have to clean it up. So I'm just going to bring the 2 in. Again, this is a formal operation. This is a set. You're just saying 2 times the elements in the set is you can multiply each function in here by 2. You can bring these together. This is really, again, it's just a formal operation, what we're doing here. Again, this set minus this, it means this. And then you just wind up cleaning everything up. So this is where we left off, right? And again, these notations all mean exactly the same thing. All mean exactly the same thing. So this is a set, this is a set, this is a set. Everything in here looks like this function plus some constant. And that's what the general solution is. It's a set of functions. So next thing we do is we find the particular solution. Right? We want one of these functions, a function that has this form, one of the functions in this set, and we want to pick the constant such that it meets our initial condition. Right? So we have infinitely many choices. These functions all satisfy the dynamics, and at this point we need to satisfy the present state of affairs, the initial condition. So how do we pick that? Well, all our functions specifically look like this. Again, see, I'm using the small c, so I have to determine what this constant is. All the functions have this particular form, right? Now, all we're going to do is substitute in our starting point, 1, and notice we have all this data. F of 1 was given as 2/5. And now it's just algebra to solve for c, right? So just do the algebra, and we arrive at the fact that c equals 2. That's the particular constant we want. So our function is going to be this. See, everything's determined now. It's a specific function. It satisfies the dynamics of the problem, and this fudge factor satisfies our initial conditions. And you can check your answer. That's the nice thing. If you take the derivative of this, you'll see that it satisfies, again, the dynamics. It equals, the derivative is the original derivative specified in the problem, and it satisfies the initial condition, so you can check that for homework. So this, again, is going to be the way we're going to solve these problems. Now, this is what we did before, only, the way we did it before was very cumbersome. It's just you reverse engineering. We really didn't have the machinery set up in the form of the antiderivative notation to handle that. But this essentially does exactly what we did before. If you care, you can go back and relook at it. Only it does it in a more efficient way, right? It sets it up as antiderivatives versus just reverse engineering the differentiation rules. And then we're just going to work a lot of these problems and gain some experience. So what do we really do with these problems? We're going to use the tangent line or the Riemann sum approximation to solve them. And I said, this is fairly easy to do these days, certainly for a function of a single variable. So it's very efficient. Again, we're not going to have time really to put into this, but in your career, I'm sure this is what you're going to see. Okay, so now the third problem we're going to handle is we're going to solve definite integrals using the evaluation theorem. And again, how are these problems going to work out? Well, let's take a look. So now notice we have the definite integral here, and the definite integral is a number. And again, all the work is really in the indefinite integral stage. So let's take a look at this. So the first thing is find the indefinite integral, and this is what we've done. This is what we've done already. So this is the root function. And then we'll just evaluate the definite integral using the evaluation theorem, which says this. So notice all we have to do, all the work is in this step with the indefinite integral. We just have to evaluate the indefinite integral at the ends. Right? So, you just evaluate it at the ends. And again, this is the prototype of how we're going to look at problems. So these are the three types of problems we're going to look at. We're going to look at the indefinite integrals, we're going to look at their application to initial value problems, and to definite integrals. So these are the types of problems we're going to explore for the rest of the semester.